Check, check. Good morning, everyone. My name is Thomas Rupp, and I'm very happy to present at this unique virtual OTS in the pre-conference CMC workshop. And I'm going to speak about the categorization and the origin of oligonucleotide impurities. A big thanks to the organizers for inviting me to speak here. The views expressed in these presentations are mine, and they do not necessarily represent those of any regulatory agency. Any categorization of impurities is up for discussion on a case-by-case basis. So what are, or how to define oligonucleotide impurities? Strictly following the ICH guideline Q3, any molecule that is different than the parent molecule, in this case the full-length oligonucleotide, should be treated as an impurity. Easy. Oligonucleotides obviously are excluded from the ICH guideline Q3A, that's impurities in drug substances, and Q3B, that's impurities in drug product. But of course the spirit of the guidelines shall be applied to oligos as well. Oligonucleotide impurities typically exhibit similar characteristics and properties as the parent compound, which makes the categorization of impurities, or the definition of impurities, quite tedious and difficult from a regulatory point of view. On top of that, they cannot be controlled in a manner similar to impurities in new chemical entities, in small molecules. One of the reasons is that these product-related impurities in oligonucleotides tend to have safety profiles that are similar to the intended drug. One example here would be the single phosphodiester exchange in a phosphorothioate oligonucleotide. This oligo will have the same safety profile, and it might even have a similar activity to the full phosphorothioate. In 2017, the Oligonucleotide Safety Working Group suggested in a white paper a classification of impurities into 4 different impurity classes, and assess the safety and the potency of impurities only for impurities that are classified as critical. The classification of the impurities in the Capaldi et al. Publication looks like this. The first class, or class 1, these are impurities that are also major metabolites, which means the structure and the sequence are the same as the parent compound. And examples for that would be impurities that lack a single or multiple nucleotides from either the 3' or 5' end of the parent molecule. Impurities formed by incomplete conjugation in a conjugated oligonucleotide, which means a conjugated oligonucleotide, for example, with a GalNAc or a cholesterol that misses the GalNAc or the cholesterol, would be a class 1 impurity. And then, of course, in siRNA, a parent single-stranded impurity of the double-stranded oligonucleotide would be a class 1 impurity. Safety assessment of these impurities is usually not required, or as they are major metabolites, they're covered in the tox studies anyway. Class 2 impurities are impurities that contain only structural elements that are found in naturally occurring nucleic acids. This is, for example, the phosphodiester impurity in a phosphorothioate oligonucleotide, or 2', 5' linked riboses in RNA. As they are natural occurring structural elements, they also do not require a safety assessment. Class 3 impurities are sequence variants of the parent compound. This is, for example, N-1 internally, missing one base, N+1 one additional base internally, and deaminated impurities. These could also occur naturally, and they are just sequence variants. So the oligonucleotide safety working group suggests not to assess them in a safety or tox study. And then we come to the critical impurities. That's class 4. These are impurities that contain structural elements which are not found in the parent compound or in natural occurring nucleic acids. These are process-related impurities, mainly process-related impurities or raw material-induced impurities. And these are base modifications, backbone modifications, depurinated species, for example, and unidentifiable impurities. These require safety assessment if they are above the set threshold for impurities. On this slide, I'm just explaining what I just explained in writing, so I just skip that slide. Here you see the decision tree for the impurity classification as suggested by Capaldi et al. By the Oligonucleotide Safety Working Group. I'm not going through this for the sake of time. This is just for your reference, and it's copied directly out of the publication. Where do these impurities come from? In a general oligonucleotide manufacturing process, we have the upstream with the synthesis and the cleavage and deprotection, and we have the downstream with the purification, desalting, and lyophilization. And in case of siRNA, between the desalting and the lyophilization, of course, there is another annealing step. In case of a conjugate oligonucleotide, the final step before the purification would be the conjugation reaction. If we look at the general oligonucleotide manufacturing process in a more visual way, you have the raw materials here on the top left corner. You have the synthesis cycle here. Following the synthesis is cleavage and deprotection. In case of RNA, a second deprotection, then a crude desalting or precipitation, depending on the process. You've got a purification, fractionation, pooling, second desalting, annealing, if it is an siRNA, freeze drying, and finally the storage. All the yellow highlighted steps could create impurities. So if we take these impurities and try to relate the process-related impurities to process steps, I've made this list here, and I've classified the oligonucleotides here as well. We have the internal deletions. These come from a resin. If the resin, for example, is a nucleoside-loaded resin and missing the nucleoside, of course, it comes from the synthesis and from the deprotection. Potential classification would be a class 3. Double couplings, these happen during the synthesis, or if the titillation wash, during the coupling step, or if the titillation wash step is not sufficient. They are also, according to the categorization table, they are also potentially class 3. Branching. Branching, for example, on inosine or on the, as described on the O6 of guanosine. These are related to the synthesis conditions, and the branching is a non-natural occurring structure, and I would classify that as a class 4, as a critical impurity. Even though they have the same sequence, the branches, but it's a structural branched molecule, which looks completely different than the parent molecule. Terminal deletions, N-X, due to the resin missing the nucleoside, storage, degradation during storage or degradation during handling. These are classified as class 1. Hydrolysis product, phosphorothioate exchange for a phosphodiester. These happen during the synthesis, during oxidation step, if there is a mixed backbone oligonucleotide, phosphorothioate, phosphodiester. They also happen during capping. That has been shown by Capaldi et al. In his one of his, I think it was a presentation at the Eurotides 2014, and they happen during storage, especially when the oligonucleotide is stored in solution. These are class 2 impurities. Bases could oxidize. That could happen during the oxidation. If the oxidation is overreacting, that's a class 4 impurity because it's a non-natural occurring base modification. Strand schism, depurination happens during the synthesis, during detritiylation, class 4. Backbone modifications, these happen during deprotection, during detritiylation, during thiolation, and during storage. During storage, for example, especially for 2' fluoro-modified oligonucleotides which lose AHF, and you see that in the mass as -2. These are class 4 modifications, of course. A-basic base fragmentation happens during deprotection, detritylation, detritylation, purification, and storage. Base fragmentation can be classified as class 3. Base modifications, deprotection again, syntheses during the capping, starting material impurities. These are classified as class 4. The capping impurity would be the triazine plus 85 impurity, which has been described in the literature. Acetonitrile adduct, CNET, everybody has heard about that. It happens during the deprotection with ammonia. It's a class 4 impurity. Transamination is N plus methyl, especially the C base. It's plus 14. It's a deprotection related and happens mainly in ammonia methylamine or just plain methylamine deprotection. Residual protection groups, especially the isobutyl group on the G, which is the plus 70, happens in with either due to incomplete deprotection, not well chosen deprotection conditions, or it's a modified starting material. Single strand impurities in siRNA happens during annealing, and that's class 1 impurity. This is just an excerpt of potential impurities and the process steps that these are related to. But as you can see, all impurities can be directly related to process steps or to starting materials. And with a crude analysis of the oligonucleotide after the synthesis, after deprotection, you can directly identify critical process steps and go back and optimize these. And another thing that is worth mentioning is a lot of class 4 impurities happen during the deprotection. So the deprotection step is one of the most critical steps. On the next slide, on the next slides, I'm going through the individual process steps, and I've drawn some potential impurities and given the references. Here, first step in the synthesis is the detritiylation. During the detritiylation, A-basic sites could happen, depurination could happen, and also a raw material impurity, the chloral, could happen. Chloral is plus 145, and the A-basic sites depend on the base that has been cleaved off on the purine. Coupling step. During the coupling step, mainly the main impurities that you see are in an overreaction, the double coupling or branching. Under reaction leads to N-1, and these are the most impurities that you see here are raw material induced impurities by critical and reactive impurities from the amidite manufacturer. For example, if you synthesize the 2'-Mo oligonucleotide, the main impurities from the raw material that you see are 2'-O, 2'-ethoxyethyl impurity, that's mass plus 14, that's an additional methyl group in here, or the 2'-methyl impurity from the amidite manufacturing process, and this is just the mass minus 43. Another impurity that's quite common is the cyanoethyl amiditophosphate modification. That's a plus 80, and that's also a raw material induced impurity. As you can see, there's an additional phosphate in the backbone. Capping. Capaldi has shown nicely, and also other people at Ionis Rodriguez have shown nicely that capping leads to quite some significant impurities. I've listed them here. Overreactions lead to decreased yield, then to the ADP, IDP, AMPA impurities with a mass of plus 41, plus 96, and plus 89 respectively. Capping also leads to PO impurities. And a raw material induced impurity is the triazine contamination of the NMP. That's the plus 85 one that has been described by Honeywell in 2013. Here are the structures of these impurities at your convenience. The next reaction is the oxidation reaction. Overreaction here leads to base oxidation, to a PO in a phosphorothioate oligonucleotide, and it also leads to a C-phosphonate formation during the next detutelation step, which I will show on the next slide, which is the sulfurization. And here you can see, for example, the G oxidation that has been described by Choi and Fute in 1995. That could happen, and that leads to a mass plus 16. Sulfurization, same thing. It's an oxidation reaction with the sulfur. This is the structure of the 4,4-dimethoxytriethyl C-phosphonate impurity. The oligonucleotide, the cyanoethyl group, basically is replaced by the DMT group, and the oligonucleotide extends here and here as normal, and that gives a mass of 367 or 383 respectively, depending on whether it's a phosphodiester or phosphorothioate. These are the deprotection related impurities. As you can see, here is base fragmentation on the U base, ribo U base. You can see minus 52 and minus 94. Transamination reaction, the plus 14 impurity, cyanoethyl adduct, the plus 53 impurity, and the residual protection group at the guanosine. And if we look at that in a ion pairing, higher resolution ion pairing chromatogram, this is a slide from Capaldi's Eurotides presentation. I do not have better data, that's why there is stuff on there that doesn't belong to here. But here you can see that the N+1 and the branching are clearly seen after the main peak. They have a retention time of greater than 1. The N-1s are located here. Of course, they have a retention time of less than 1.0. The A-basic impurities would elute just in front of the main peak, with a little distance in front of the main peak. The PO impurity in a phosphothioate oligonucleotide elutes just next to the main peak. Sometimes it's also covered under the main peak. The main peak usually also hides depurinated species, because they have the same retention time, or closely retention time, as the parent molecule. ADP is here, CNET is here just after the main peak, IDP is here, AMPA modification is here just after the main peak. The 2'O ethoxy ethyl impurity elutes here just in front of the main peak, and the 2'O methoxy just elutes here. So you can see by the position in the ion pairing chromatogram, you can also support your mass spec data and identify the impurities. That's another chromatogram. Ingo Röhl from Axolabs gave that to me. Here you can see the separation between N-1, 3', N-3, 5', they elute at the same peak. N-1, N-2, 5' elute at the same peak. PO impurity just next to the main peak. Again, N+G next to the main peak with a retention time greater than 1. CNET plus 14 methyl would also be here in that region, and plus 85, the triazine impurity can be seen here. Right, that was my presentation. Briefly, the summary. Again, ICH-Q3 states that any molecule that's different than the parent molecule should be recognized as an impurity. Oligonucleotides are excluded from a Q3A and Q3B, and so there is no explicit guidelines on process-related impurities available. These have to be discussed on a case-by-case basis with the authorities. And in 2017, the Oligonucleotide Safety Working Group suggested a classification of impurities into classes according to the nature of the impurity, and assess safety and potency only if classified as class 4, and of course detected above set reporting and characterization thresholds. And the analysis by high-resolution ion pairing LCMS allows the tracing of the origin for each impurity back to the respective process step, which then can be optimized. Thank you very much for your attention. Questions will be addressed later.